If no, let's go to finite volume. So finite volume solves conservation laws. Du dt not equal to anything but plus the derivative of a flux with respect to x equal to 0. This is the kind of a first order PDEs, not first order, the scalar PDEs in one dimension that the finite volume can solve for you. And this kind of PDEs develops what's called the characteristic lines. So if you plot the solution in space and time plots, the characteristic lines are lines that follows constants in space-time, and the slope of them are inversely proportional to, so if I write the slope as delta x, delta t, so delta x over delta t is going to be df du, is the derivative of the flux function with respect to u, right? Okay, and in particular, if we have this Burger's equation, so Burger's, not this, Burger's equation, du dt plus u times du dx equal to 0, which can be written as in the previous form if you choose fu equal to u squared over 2, right? By applying chain rule, you differentiate the u squared over 2, it becomes u times du, right? So you get this. So then delta x over delta t, the reciprocal of the slope of these characteristic lines are going to be just a u. So u positive, you have slope towards the right, u negative, you have slope towards the left. And the solution is constant. That's the important thing. The solution is constant along characteristic lines. All right. So now, how do you derive the integral form of a PDE? And the integral form can be easily derived from this type of conservation law, PDEs, because when you integrate du dt, right, over, let's say, over any interval between left and right, you get the derivative of the total integral between these lines. And when you integrate the other term, the derivative of a f over x, so integrating a derivative in x, this is x and the integration is in x. Unlike in the previous, I'm integrating x and differentiating t. Now I'm differentiating x and integrating in x. What I get is fu, the difference between right and left, right? So this is really, you plug this into the equation, this is really the integral form. And the integral form gives rise to the finite volume scheme, right? The finite volume scheme is basically splitting the space into a finite many volumes. And if I have a solution like this, I'm just approximating the average across these volumes. Okay, and another thing to know is how does the PDE develop discontinuities? That is when the characteristics they are non-constant, and if they merge, this is going to become a shockwave, a discontinuity. And the discontinuity moves with a speed that is quite similar in spirit to the slope of the characteristics. So in the sense that if my, okay, first of all, unlike the characteristics, the speed of a shock may be different. So I should be writing dx over dt of a shock. It's actually equal to the delta f over delta u instead of df du, right? for DFDU, I'm looking at a smooth region of the solution, so I have DFDU. Here I'm looking at a discontinuous shock. So delta F is the difference in the flux across the shock, and delta U is the difference in the solution across the shock. All right, and just a simple conceptual knowledge of how finite volumes works in 1 and 2 dimensions is good to know. And what are some common numerical fluxes for scalar equations? That is, you can take the average of the two sides of an interface, right? So the numerical flux means I want to approximate the value of the flux on the interface while I only know the averages of the solution at the two sides. I can average the solution over the two sides and apply the flux function. If that works if I'm in a smooth region or when I have a discontinuity, right? The appropriate way is to apply what's called a Riemann solver. That is to figure out if I actually have a discontinuity, what would the solution do over there? And for scalar conservation laws, it usually leads to the evaluation of the upwind direction, right? So you take the value, you take the average, cell average, or on the upwind direction, and evaluate the flux over there. All right, that's some basic finite volume questions to ask. Any questions?